remember that first our friends Bruno Zumina and Mikey Gayer invited us to their house somewhere uphill here. And it was night, and all of these airplanes sitting in the bay nearby, and everything shining. And I said, my God, that's just a dream. So I'm on this state, well, for 25 years already. I'm very happy to be here and to visit our friends again and again in this place. Okay, so the subject today is universe or multiverse. And the reason why we consider these two words together, actually, the concept of multiverse is pretty recent. It was all the time universe in a sense, it is still remains so, but there's something else which appeared in our lexicon recently which require new words somehow to understand, explain what we mean by that. And it all started, well, substantially started with the invention of inflationary cosmology. But on the other hand, the way of asking these questions go back in some way to this long statement which was for your viewing pleasure already for quite a while, and that belongs to Albert Einstein. He read it in his autobiographical notes, which were supposed like his obituaries. He was writing it himself about himself, and okay, well, so that's what I think. Well, so what he said is that I would like to state a theory which at present cannot be based upon anything more than a faith. That is interesting. When the person says something which he is, well, deeply believe in, and on the other hand, he admits that there's a caveat here. So let's do it softly, okay? So it was a desire which actually in the heart of all of us to find some simplest explanation of all facts of our world, and simplest but no simpler than the truth. Okay, so then the question is, can we do something like, well, finding one explanation which will explain just everything, which will allow to predict everything, not only to predict well, what happens with the next president, but just everything else. Oh, you consider multiple choices. That is what the talk is about, right? This is about the multiverse. That's many possibilities, some of which are fundamental and some of which are environmental. Some things happen without any fundamental reason, and maybe that's why we see part of the universe which we live right now the way we are. But let's try nevertheless to pay attention to this idea that let's try to do our best in simplicity, and maybe even in the possibility that there will be one unique theory which is the only one which is logically possible, and that would be great. So we were trying to do it, and one thing which we were trying to do as cosmologists is to address at least one part of this story, and that is when we look to the right of us and we look to the left of us, the mass of the electron is the same in that galaxy and in that galaxy. So somehow distribution of galaxies over the sky is also uniform. So this is experimental fact. We want to understand why is it so, why the laws of physics do not change when we go from one place to another, why the properties of the universe do not change, that is uniformity of the universe. So we started trying to explain the origin of this, well, experimental fact that we observe right now. And the way to explain it was inflationary cosmology. And then when we start developing it further and further and further, we did part of the job, and then suddenly we have seen that actually this is not exactly what we are planning to get. And that will be what I will be talking about today. So here is some situation what we had about 30 years ago, a little bit more than that, when we had this Big Bang theory, which at that time was extremely popular. We knew that it must be true because it was explaining so many facts of our life. But there were some problems about it which were kind of metaphysical. And one of these metaphysical problems, what was before the Big Bang? Because, well, when things banged, so what was before the bang? And when you open the textbook by Landau and Lipschitz and read it, and that was how we learned, general theory of relativity. In Russia, there was a book where it was described, and the author said that the solutions of Einstein equations cannot be continued to negative time, to the place where, well, not zero when everything started, but before that. And because it's impossible to continue this equation, it does not make any sense to ask where the universe came from. On the other hand, sensible or non-sensible, but everybody continue asking. Why is our universe so uniform? So the answer to this question, or attempt to give the answer, was suggested by Albert Einstein, who said this is cosmological principle. The universe is uniform. Actually, Newton also used the same principle. At some time I didn't know that this was a principle which these people used, so I used to make a joke that some people who don't have good ideas, they have principles. But then I understand that I should be probably shut up. And here is another question. Why the universe is not exactly uniform? Because you have galaxies. And galaxies are very important for our life, and they are non-uniformities. So you cannot just say that our universe must be uniform. Oh, sorry, galaxies, but don't pay attention. So this is then not really a matter of principle, like the person who takes small bribes. This is not a person of principle, right? Okay. So why the universe is isotropic? Isotropic means, well, everything that we feel for granted, that the universe in this and in that direction is approximately the same. So the universe looks like something spherical instead of being like a cucumber. Okay? So why not? Now, this is a physical question. We know that the universe is isotropic. What I mean by that is not only all this abstract thing about cucumber or whatever, but like, why don't the universe rotate? The universe may rotate, nothing forbids it to rotate. People measure it, whether it is rotating, they didn't find any rotation with a huge accuracy. Why doesn't every galaxy rotates? Our solar system consists of planets rotating about the sun. Our universe doesn't. Okay? Why there is no axis in the universe? Well, this is not so certain. Maybe some of you have heard about axis of evil, and I'm not talking about countries, I'm talking about something in the sky. Anyway, so it is isotropic with enormous accuracy. So why is it so? Why all of its different parts start expanding at the same time? Because if the universe, well, was big, like the universe, okay? So this part and this part did not know that it's time to start, because it was time zero. So they could not exchange information that it is already time to start. So who gave the signal? Well, this is not the way physicists like this question to be posed, who gave the signal. So when I was reading it, when I was a student, I remember I had a flu, and I was reading this, the journal explaining the theory of the Big Bang, that all different parts of the universe start expanding simultaneously. I thought, oh my God, I guess I am really sick, because I really don't understand what it is. How the universe could have started expansion simultaneously, who gave the signal? And I thought that maybe when I will grow older, I'll go to my professors, ask the question, and they will explain me what is wrong about it. And then when I grow older, went to Moscow State University, and I learned that professors did not know that the question existed. Why the universe is flat? What do I mean is that in school they tell us that parallel lines are parallel, they do not intersect. That's if Klee told us about that. Then we go to the university, they say that space is actually curved, and parallel lines can intersect or can diverge at infinity. There are two different possibilities that our universe is closed, and it has geometry similar to the surface of a globe. Parallel lines which are parallel near the equator, they meet at the south and the north pole of the Earth or the universe. So then why don't we see these parallel lines intersecting? So they could be parallel, but not for long. And apparently it's a difficult, very difficult problem to solve. This being flat is characterized by some number. If the universe is closed, that this number is bigger than 1. If it's open, that it's smaller than 1. If it is exactly 1, then it's flat. So people thought that maybe if we start with a universe with a reasonably flattish, then we get eventually our very flat universe. But what later we have learned, that you must have started with a universe which is extraordinarily flat to get anything close to flatness right now. So there was a problem. And then there is another problem which is equivalent to this one, even though it at first glance seemed very different. Why there are so many people in this auditorium? And the answer to this, well, so many people in Berkeley, and some of them decided to come. Why are so many people in Berkeley? There are so much more people on the Earth, and some of them live in the US, and some of them live in Berkeley, and some of them decided to come. Why are so many people on the Earth? Oh, you know what? We just discovered 1,000 different planets, which are very similar to our Earth. We're actually learning that almost every star has a planetary system, so like ours. So in our galaxy, there are approximately 100 billion stars, okay? And some of the stars have planets, some of the planets have people, and some of the people live on the Earth, and some of the Earth, whatever. And they came to lecture. And then the question is, why there are so many stars in the galaxy? Well, do you know how many galaxies in our part of the universe? 100 billion galaxies. And then everything repeats. And then the question is, why the universe is so big to accumulate all of these galaxies, etc.? And the answer is like father tells his child, shut up. The universe is big because it's a universe. So this is what we knew about the universe. We did not really know why it is big. It was just big. Okay? So what we learned that it is hard, and we still do not have any convincing answer to this first question. But the existing answer mostly they are rotating about using some of the advantages which inflationary cosmology provides us with. And as for all of these other questions, answer to them have been provided by inflationary cosmology. So this happened, these first models of inflation, they have been invented more than 30 years ago. During 30 years ago, we changed our own opinion about it. At first, it was like wild dream. At second, it was a dream. And third, it was a reality. And now it is certainty for some of us. Well, so this is what I'm going to tell you about, because yes, you tell about this, about certainty, somebody else, and somebody will start laughing. So let's try to explain. This is the simplest model which explains not necessarily correct, but it is a good model explaining the nature of inflationary theory. So what we have here, we have something which is called scalar field. Sorry, we will need to use this concept, but for a while. It will be painless because nobody will be examined later. But the idea is the following. You have heard about this God particle which was found at LHC, right? Okay, this is Higgs particle. So there is a field excitation of which this Higgs particle is, and this is called Higgs field. And that Higgs field is the simplest example of the scalar field. So it does not make your life easier. Here you have 110 volt in a socket, okay? So if you have just 110 volt all over the auditorium, you will not be, well, shocked by that. It will be just another vacuum state, no current. You need to have 0. 110 and 0 you have current, okay? If you have 110 here and 220 in Europe, God forbid touching both ends, these two different places of the world. So difference matters. But if you have something potential, electrostatic potential, all over the United States, there will be no current. Okay? Now, scalar field is something like that, except for it may have energy density sitting in it. So the larger scalar field have energy density. And also, it changes properties of every particle in your body. In particular, Higgs field is the reason why all particles which we are made of are not massless, and that's why we are sitting here, not flying as light with the speed, okay? So Higgs field is, we think, have been discovered. The field which drives inflation, we do not know. There are some models which even allow inflation to be driven by the Higgs field. But at the moment, let's just study the simplest scalar field, which has energy, potential energy, proportional, for simplicity, to the square of the value of the scalar field. Once again, it is not a required knowledge. And you may hear it like a song which tries to convey you the main set of emotions which we have about it. So we have this scalar field which drives inflation, and if it has even the simplest potential, like a parabolic potential, like the potential of a pendulum, then this simple model explains why the universe may expand exponentially in the very beginning. Well, actually, this was not the first model of inflation. The first model of inflation, as we have heard about it, was suggested by Alan Guth long ago. And the idea was explained like that. So let me first tell you the emotional part of this idea. Okay? So suppose you have a box filled with candy. So you have 1 cubic meter filled with 1,000 candies. Okay, now the universe expands, the box grows. So when the size of the box grows 10 times, the volume grows 1,000 times, and you still have the 1,000 candies. So 1 square meter, you have just 1 candy. And then the universe continues expanding, and less candies you see, right? Okay. So that was the problem with the Big Bang, because when the universe is expanding, density of matter becomes smaller and smaller and smaller, and the universe slows down. The Big Bang is not so big. Now, inflation tells you approximately this. Let's take the box and fill it with heavy nothing. Okay, so it's like a vacuum, which nevertheless have some vacuum energy sitting in it. Energy density. So per 1 cubic meter, you have some special property of the vacuum which has some energy in it. And this is not a fake idea, because people from here in particular have discovered in '98 that vacuum energy in our own vacuum, in our own universe, vacuum energy density is not equal to 0. This was, I believe, one of the most important discoveries of the 20th century. So I'm proud to be in the same, part of the Earth where this happened. Okay? Now, so we know that energy density of vacuum is non-zero. Let's just consider it. Let's take what is the consequence for that. So you have 1 cubic meter filled with nothing. Okay? So you expand it 10 times. What is inside? Nothing. What changed? Nothing changed. It's the same nothing inside. So per cubic meter, nothing changed. But now we have 1,000 of these cubic meters. So the total amount of matter there have grown 1,000 times. Okay? Once again. So you start, because this is a trick. You start with heavy nothing, you expand it, and the total amount of the heavy nothing grows. And as a result, if you continue expanding, and at some moment this decays, per 1 cubic meter you produce 1,000 candies, then because the total number of cubic meter will be huge, and in each of it will be 100 or 1,000 candies, you can feed all babies in the universe. So that is the basic idea of inflationary theory. You start with something similar to vacuum, not exactly vacuum, but some similar, and then you do the job. So this idea, not about candies, but something similar. This was the basic of all the inflationary model by Alan Guth. But then, of course, you may argue, but if you have really empty anything, what is actually expansion? Because if you do not have any candies there, you don't have any marks, it's just heavy nothing, then it expands and you do not even know whether it expands or not. Okay? So this was one of the reasons why original model of inflation did not actually work. And it was replaced by some other model and some other model, and eventually models which are used today, they're based on something more sophisticated, like the scalar field story. So to explain the scalar field story, let's assume that in the beginning, in some parts of the universe, scalar field was sufficiently large. So what does it mean? And now this is just to scare you a little, but also to show you that when I was talking about this heavy nothing, you are not obliged to take my word for it, because it sounds like the man is drunk. Okay? But these are equations, they are very simple. They have been checked by scientists who know what scalar field is, and they are actually pretty simple. This one is somewhat simplified Einstein equation describing the motion of the universe. This radius of the universe, dot, means the speed of expansion of the universe, divided by its size. This is called Hubble constant. And it is proportional to energy density of the universe. Okay? So then this other equation is equation for the scalar field itself. It tells you that if you start with scalar field, that start moving, and this equation tells you how it is moving. And this, by the way, is equation for harmonic oscillator. So harmonic oscillator, everybody who had some memory of your school education in physics know that this is acceleration, this is a force. And dot is just to show you this is acceleration. Two dots. And one dot means this is velocity. Okay? So without this term, it's just equation for oscillator like that. But if you add this one, it's like oscillator with friction. If friction is large, the body moves down very, very slowly, very, very slowly. For a long time, it remains at the same distance from equilibrium position. This is this friction term in the equation for the scalar field. And friction is large when Hubble constant is large. So when Hubble constant is large, friction is large, and scalar field practically does not move. The universe expands, and vacuum practically does not change. So it's empty space filled with scalar field phi, it's expanding, and vacuum energy practically does not change. So this is a logic of inflation. If scalar field is large, Hubble constant is large, friction is large, field moves down slowly. If it moves down slowly, Hubble constant is nearly constant. But Hubble constant, according to Einstein equation, is this, and this is the simplest equation of mathematical physics. You solve it, and you get exponential expansion of the universe. I am not, well, forcing you to check the solutions. They are really very, very simple. I am just pointing it out to you that the basic idea of inflationary universe is very primitive. I do not know why people did not come to this idea like 50 years ago, because all equations were known. Well, there are some mysteries of the universe and of human nature which remain mysteries. But this is very simple indeed. Now, the gain of this idea, a newborn universe can be as small as 10 to the minus 33 centimeters, can be as light as 10 to the minus 5 grams, and then after that, you wait 10 to the minus whatever 35 seconds, and boom, you get all of your universe. In general, there are some ideas even how to create the universe from nothing at all, but I'm not going to discuss it right now here. It's for questions after the lecture. Okay, there are even a question, how can you actually create the universe now in a laboratory? Okay, it's also for the extra questions. So now, you start with this universe. This is smallest size which you can imagine, because the smaller size, you can not measure anything there. Your rulers will be bent. You'll forget everything that you measure. This is called Planckian length. Very small mass, and you wait this small time, and you get this. This is the universe, which has a size 10 to the degree, and this is a big number. Okay, and it really does not matter in which units. Okay, because it's bigger than anything you can imagine, and we live in some tiny, tiny fraction of it. And that is why we see the universe is so uniform. We start from the red, it's red all the way out. Okay, you start from something curved, you stretch it, and the universe becomes uncurved. You have parallel lines here meeting here, but we cannot see so much, because the maximal distance, which we can see right now, is the age of the universe, 10 billion years, or 14 billion years, or who cares? Okay, 14 billion, 13.8. Well, multiplied by speed of light. That's the maximum which we can see right now. Well, actually, it's not quite correct. There's some coefficient there, but anyway. So we cannot see all of this. We cannot see these parallel lines intersecting. That's why parallel lines do not intersect. That's why Euclid is right. So after all of this time, we have a very simple idea which finally explains this idea of this 2,000 years ago when the person told us that parallel lines cannot intersect. Now we know why. Okay? Now, on the other hand, this scenario, which solves many of the problems which I listed you before, why the universe started at the same time simultaneously, because it started from this tiny spot or whatever. So and then everything emerged and all conditions were everywhere the same. So we can solve all of these problems which I mentioned on one of the first pages. But then the question is, we may overdo it, because if the universe stretches so much, then your Himalaya is stretched into flat area and there will be no alpinism, whatever, because everything will be absolutely flat with this expansion. So we need to get galaxies. Well, happily, during the time when this theory was invented, it was also found that quantum fluctuations during inflation, quantum fluctuations which exist everywhere in this room as well, during this very rapid stage of expansion, they were stretched to an enormous distance. And while they were stretching, they were frozen because of this friction term, which I've shown you, 3h5 dot, never mind. So they were frozen, and then new fluctuations were produced on the top of the previous ones. So previous were frozen, new were produced, previous were frozen, new were produced. What is this mechanism? You take something quantum, and you get something classical. And just before coming here, I had discussion with some people here about this invention of laser. So what laser does? Laser takes something quantum and produce classical beam of light, coherent, containing many, many particles pointing in one particular direction. What our universe does, it takes these quantum fluctuations and stretches them. And from something quantum, it produces something big and classical, which is going to be our galaxies. Our galaxies produce like that, but the difference is this laser produces the green beam, okay? So it's just green beam and green beam and green. Actually, this laser maybe have some red heart in it, but there's something converting it into green, but never mind. It is green now. What universe does, it produces these quantum fluctuations, it expands them, stretches them, and then redshift them. And if they produce it blue, they become red. And then they produce another blue, and they become red. And the ones which become red, they become infrared, and then very, very long wave, and then you produce all wavelengths. And as a result, you produce all collection of all these galaxies and everything which we see right now in the universe. That is the best and the only theory of producing seeds for emergence of galaxies which is presently available. It's science fiction. You create everything from 10 to the minus 5 grams of matter. And then you produce galaxies from quantum fluctuations. You must be totally insane to do this. Okay, but then how is that? You have 10 to the minus 5 grams of matter. We know that energy is conserved. So you cannot produce 10 to the minus, or from 10 to the minus 5 grams of matter. You cannot produce everything. I must be cheating somewhere. Well, the answer to this question is actually quite paradoxical. It's like that. The total energy of the universe actually is exactly zero. You have energy of matter and negative energy of gravity. And positive energy of matter during inflation start exponentially growing. Negative energy of gravity start exponentially growing, but it's negative. The sum of them is as small as it was originally. It is conserved, but it is just split. So inflation is exponential instability of our space with respect to the division into matter and the energy of gravity. And that is the trick. So it sounds very strange and philosophical. But forget about philosophy. Here are your equations. So it is possible to check it and do philosophy later. So that's why I decided to check, to show you this equation, to show that you would not trust me if I tell you that we are violating energy conservation here. But then here are equations, okay? So to check all of this, we launch satellites. One of these satellites, and people here also know these heroic developments many, many years ago. Some part of it was here, mostly in Berkeley. So this was Kobe satellite, which was measuring the first imprints of these quantum fluctuations on the sky. Then it was WMAP satellite, which continued this tradition, and they found this with much greater accuracy. And then later it was Planck satellite, and we're still getting new and new information. Planck satellite already stopped producing new results, but we're learning what they told us about our universe. So what they produce looks like that. So these are tiny, tiny spots, distribution of temperature on the whole sky. So we take all the sky that we can see, the most distant parts of it, okay? And we measure temperature of radiation which goes to us from different parts of it. It is an echo of the Big Bang. The universe was hot at some stage. Then, when it was expanding, it cooled down. It has the same temperature in all possible directions. It is 2.7 Kelvin. But if we measure it carefully, we will see that actually it's like 1,000th of a Kelvin more hot in this direction and 1,000 colder in this direction. And that's because our Earth moves with respect to the universe. And therefore, in the direction in which we move, we regard photons hitting us like more energetic. So these parts seem to be a little bit more hot. So we can subtract it from our results. And then everything becomes uniform again until we increase accuracy of measurement to approximately 10 to the minus 5 Kelvin. That's just incredible. That is the moment when even theorists like I start to respect my experimental study. So this Planck satellite people produced this image, and they were trying to, well, explain general public that this is what we get, and these are our magnificent results. And then the public asked them, so how much your experiment cost? And they would say, oh, approximately $1 billion. $1 billion for that? I will just go to Home Depot and I will spray you everything much cheaper, because this doesn't seem to contain any interesting information. So, and actually, this is not a joke. These people would come to me and say, what can we do? Because we cannot excite anybody by this picture. I say, just tell them that what you see, each of these spots, you are seeing right now quantum fluctuations produced at the 10 to the minus 35 seconds, like a billions of a billions of a billions of a second, more than that, after the moment of creation of the world. And then it is stretched on the largest size available, the largest photographic plate which has ever been possible. And then you are watching it right now. These quantum fluctuations, they are responsible for galaxies, for creation of the structure of the universe. This is more magnificent than any other painting which you can buy for whatever money you can want to spend everywhere on the earth. Okay, and then one of them told, yes, I made this mistake. One person belonging to Planck, I made this mistake. And I told once at the press conference that some of my colleagues would sell their children to see this picture, and they still cannot forgive me that. Okay, so now the latest Planck data, and this looks, oh yeah, you need to have it with a really good resolution. So what you see here, it's like, oh my God, I cannot even describe it. So you need to have a much better focus. You will see some like fluxes moving here, and not fluxes. This is polarization of these perturbations of CMB. So you had this incredible accuracy to see the small spots. Now we see also that light coming here is slightly polarized. This is called E mode. Okay, this is already incredible, advanced. And then people are trying to find something else which is called B mode. More about this later. On the basis of this, Planck produces, see these blue spots here? Okay, these are experimental results of Planck, which tells you how these spots are distributed. How many large spots, how many small spots on the sky. And this red line is prediction of simplest versions of inflationary cosmology. Okay? Here there's something indefinite, because these correspond to very large scales on the universe, where we see the result of the universe of experiment which happens only once. So not good statistics. But in small scales, when you cannot have many measurements, you see the agreement is enormous. And then there is something else. There is correlation for polarization. So this is not correlation between temperature. That's just, well, incredible what these people are doing. And this is the way how they use the results. So this is the flatness of the universe. Inflationary universe predict that the universe, according to Euclid, but now according to the theory, must be very flat. So omega should be 1. This will be flat universe. And now, well, in 95, 94, 96, people believe that omega is equal to 0.3. Okay? And they were telling, well, because your theory predicts omega equal 1, your theory is ruled out. And we were trying to suggest some theories which nevertheless were inflationary and whatever. Okay, so we have 0.3, let's explain 0.3. We failed. And after that, many years later, in 98, we found that actually omega is close to 1. That was the supernova data. And now, on the basis of recent Planck data, it's just 1 plus minus, and here is accuracy of 0.5% with, well, whatever. It's amazing. Now, these perturbations of temperature, they have some spectrum which is characterized by the measure of flatness. If it does not depend on the logarithm of scale, it's called flat. But inflationary theory typically predicted something, some deviation from flatness. And that is what we see right now experimentally. So this is also confirmed. Then there are some other features of this. I probably should not take your time because I also take my own time and then I will never come to the multiverse. I'm just telling you that what is going on, I'm just so lucky. And many of us are so lucky because these experiments are possible. And to see things which you predicted and other my friends predicted, you see them all in the sky, just incredible. You never believe that it's possible. But can we test inflation even better? Well, yet another Planck data release in about a year. So they did not release all of their data because they got the data. But it is very difficult to make sense out of it because there's so much of it, so many of it. It's necessary to do all correlations, and also it's all over Europe. Many countries, many institutions, and they all must agree. You know how difficult it is. Yeah, but they're doing a great job. And then another thing, and this another thing, will put some of us to, well, short-living fame, certainly. They found that there are these additional perturbations on the sky, additional perturbations, which actually the experiment was magnificent. What they did, they found not only these perturbations of temperature and E-mode, but some other more subtle perturbations, which was extremely difficult to find. People spend years sitting at the South Pole. This is freezing there. Okay?